Hi, I'm Ed Alcorta with Jenbacher Gas Engines. I'm a senior energy consultant, and today I'm going to talk about gas engines, boilers, and turbines. So if you look at combined heat and power applications where we need to produce steam, one of the most common ways, especially in the 4 to 10 megawatt range and above, has been with gas turbines throughout the last, many decades really. So this has been a common way to create combined heat and power with steam for college campuses, for industrial facilities, for large hospitals, and other applications like that. So what we have here is the fuel going in, of course, electrical power comes out. That part's relatively basic. And then you have water going in and steam coming out. The water turns into steam with all the hot energy that's in the turbine exhaust, which is at quite a high temperature, and there's a lot of exhaust flow there. So the gas turbine can create quite a bit of steam for these applications. So on the other hand, there's an alternative way to create steam, and that would be with a gas engine. So here we have a Jenbacher engine. You have the fuel going in, electrical power coming out, similar to the turbine. Here we also can capture the exhaust heat and create some steam. I will say the amount of steam that you can create with a gas engine is quite a bit less than a gas turbine. That's very true. But on the other hand, the gas engine is much more efficient. So to create the same amount of electrical power, there's a lot less fuel that you have to consume to do that. So you might be thinking, well, what if you need more steam? What do you do? How does this work? What I would say there is, with the amount of fuel that you're saving, because the engine is more efficient than a gas turbine, with that fuel savings, you can use some of that extra fuel, put it in a standard auxiliary boiler really, and create the remainder of the steam that way. And that can sometimes be a more efficient and a more flexible solution, oftentimes. So you might also be thinking, why are we talking about this now? Both of these technologies have been around for many years now, both the engines and the turbines. Also true. But what I would say is in the last couple decades, there have really been dramatic improvements in performance with a gas engine. So this represents the Jenbacher Type 6 product line from 1.5 megawatts to about 4.5 megawatts. And you can see over the last couple decades, the efficiency has increased 13 points. So that's a pretty dramatic increase. The power density, so for the same size engine, the power has more than doubled in that same amount of time. So with that combination of items over the last couple decades now, it really changes the equation on when it makes sense to use an engine in a boiler versus a gas turbine, right? So 30 years ago, the engine made much less steam. It also wasn't really much more efficient than a gas turbine, so it wouldn't have really made sense to look at it, but today it does. If we talk about some of the performance differences in a little bit more detail between the engines and the turbines. So here we have some graphs of performance at different conditions. The important thing here is really to make apples to apples comparisons. So we have an engine at brochure conditions, same with the turbine. But then what really matters is installed conditions at the customer site. That's really what the customer is going to care about. That's what matters. And so here you can see some of the power differences at the brochure ratings. Then on the installed site conditions, you can see the turbine loses some power there, especially at the higher altitudes and higher temperatures, more importantly. So I say that the hot temperatures, because you could look at an annual basis and say, well, the average temperature is so-and-so throughout the whole year. That might be an accurate way of looking at it for a whole year. But the hot day performance matters quite a bit nowadays, especially with the utility tariffs the way they are, and peak demands and peak kilowatt hours treated much differently and peak capacity than they maybe were in some cases. So here's where the engine has another advantage. It usually maintains more power at a higher temperature than a similar gas turbine. And that can make a difference with economics for that reason as well. And here we have a similar comparison, but with heat rate with a gas engine. Again, what matters is to make the comparison apples to apples on as installed conditions. So here are a couple different cases starting from brochure to as installed and hot day conditions. And here you can really see what I was talking about before, where the gas engine really maintains a significant advantage in fuel consumption over a gas turbine. This is why it can make more sense to install it to produce the same amount of electrical power and create the remainder of the steam in a gas boiler. And here we're really summarizing the way I think we should be looking at some of these projects and applications with a whole system efficiency. So not just the driver efficiency, we know that the gas engine, if we're talking about only steam, doesn't make very much steam, but that doesn't mean that it doesn't make more sense economically and in terms of efficiency. So the whole system efficiency, what I'm talking about here is if we're looking at the graph with the low steam conditions on the bottom, if we start from left to right, the gas engine you can see starts out with significant efficiency advantage. That's because of the better heat rate. And then you can see where the gas engine stops making steam and we start to pick that up with auxiliary boiler. But you can see here, even when you do that, you can still have a better overall system efficiency than a gas turbine for pretty significant amounts of steam. So that crossover point, it can vary depending on the project, depending on the engine models and turbine models and everything, of course. But in this particular example, with one of the larger gas engines, you can still create 25,000 pounds per hour before the turbine starts to have a better efficiency. So this isn't to say that engines always make more sense than turbines. If the turbine is base loaded, for example, all the time, it may come out ahead, and that's okay. I think that the numbers should tell the story in all these cases. But in many cases, that's not the case. And there are a couple other practical advantages of engines that do matter for real installations. One of those would be being able to decouple the electrical power output and the thermal power output. Since we're relying on the boiler to make a lot of thermal energy, it's okay if the thermal demand varies from electrical demand. It's easier to decouple that and still have a pretty efficient system. Also, it can be pretty redundant and resilient that way, where if the driver trips offline for whatever reason, if you're creating most of the steam with the boilers, you can pick the remainder of the production up relatively easily rather than having to refire the driver and take quite a bit of time sometimes for the steam production to get ramped back up. In summary, I just wanted to reiterate that there's more than one way to make steam. It's not that engines always make more sense than turbines for a given application or vice versa. It's more that both should be compared on an apples-to-apples basis, and some of the technology differences in the last couple decades maybe change the way that these should be evaluated and which one can come out ahead sometimes. So there you have it, a quick summary and a comparison of an overview of gas engines and turbines for these steam applications. Feel free to reach out to the folks at Western Energy Systems, Northeast Energy Systems, or myself with any questions or doubts, and we're happy to dive into these projects in a lot more detail anytime. We're happy to help. Thank you for watching.